Hi, my name is Steve Morgan. I'm the Motion Control Product Manager for Gerrie Electric. On my last video, I showed you how to size up a simple belt servo system. On this video, I'm going to show you how to add a vertical ball screw. So once you've signed in to the Motion Analyzer Cloud, if you go to your libraries and open up the last project that I did, which I called Test Sample 1, you can see where we have left off. So on this particular axis, if we go into the edit, this was the belt system that we put together. So we added a motion profile, a belt system, a gearbox, a motor, and a drive. So what we're going to do now is, after we go back to the main screen, we're going to create a new axis using an application template. Once again, we'll pick a linear axis with mechanism. This will bring us to the cycle profile editor. Now, since this is a vertical load, we want to make sure that we make the inclination to 90 degrees. Everything else can be starting at a 0 point. Select the Get Started. This will bring us to the graph. We want to add an index, so we'll put a three-point trapezoidal index in there. Let's make this move down 2 inches in 1 second. Since we're going down, we want to make sure we invert this. We'll put a slight S-curve into it, so we'll put 40%. And we're going to put a payload of, say, 2 pounds. Our coefficient of friction will be 0.01. Once again, this is where you'll pull from the manufacturer spec sheets of the ball screw. We're going to add in a 1 second dwell, because if you remember, our belt system was moving in 1 second. We'll then add another index. We'll make this again a 2-inch move in 1 second with 40%. Coefficient of friction is 0.01%. At this point, we have no payload because we've already dumped the payload. And then finally, we'll add another 1 second dwell in there. Make sure you save your work. This will bring you back out to the main screen. We'll make the voltage the same, which was 460 volt, 3-phase power. We're going to go into the mechanism and we'll add a define custom. Under the pick the type, you'll select lead screw. Let's give it a name. Call it ball screw. Okay, so now we're going to put in a 0.5 inch lead is what we use for the ball screw. We'll put in 90% efficient for the ball screw, and we'll put in a tooling weight of 2 pounds. Select the little inertia calculator, and we can calculate the inertia of this unit. In this case, it's going to be a solid cylinder. It will be made out of steel. So scroll down until you find the steel selection. We'll change the units to inches, and we'll say that it is a 6-inch long ball screw and that it has a 0.75 inch diameter. You can see that the density, mass, and inertia of the system we just entered has been placed. Select the save, scroll down, hit apply, and there's the ball screw that we just entered into the system. Make sure you save. Let's continue to the axis. Typically you don't add gearboxes with the ball screws because the lead will aid in helping the inertia match as well as providing extra torque. So from this point we should be able to search the solution. Well, you can see that all the possible solutions are on the solution list. Let's filter it by using the 5500s because that's what we're using on our belt system. For the VPL low inertia motor, you see there's 5 possible solutions. Let's narrow it down to those 5 solutions. Here you can see one of our smaller servo motors with one of our smaller drives. You can see that the inertia ratio is rather high. The average current is low. Thermal capacitor is around 29%. So what's hurting us here is the inertia ratio. If we scroll down, you can see that pretty much everything that's selected has a high inertia ratio. Well, let's see if we can fix that. So let's just select the first one on the list. We'll go to the Performance tab. You can see here that the servo is not working that hard at all. It's just that the inertia ratio at 148 to 1 is very high and will be difficult to tune. So in this case we can try to add perhaps a timing belt, but I think because such of a high inertia ratio we may want to add a gearbox. So we'll go to the Add the Gearbox selection. We were using Wittgenstein on the belt, so let's keep it Wittgenstein again. Browse for families, products, or configuration. We used a value class gearbox on the belt, so let's keep it the same. Save the selection to the axis. Okay, so let's try a search again. Once again, this may take a little while to calculate. Okay, so now we have a bunch of new solutions which are using gearboxes. So if you look at pretty much the same motor drive that we had before, but you'll notice that the inertia ratio is now 0.72, which is a lot better. We're using a 12 to 1 gearbox here. So let's scroll down to see if we can find a single stage box. See if that will help. So it looks like it's picked a 9 to 1, which is still a 2-stage box. But regardless, let's pick this solution here. So we'll look at first the torque curve. Okay, so if we look at the torque curves, you can see that our RMS green line and our peak, the red dots are more than likely the acceleration part of our cycle profile. So this guy more than likely is pretty good. And the way I know that is you look at the thermal capacity at 44%. So we're in pretty good shape here. So let's go ahead and select this one. And once again, if you look at the performance curves, you can see that we're at 44% of thermal capacity, 40% of peak speed, 34% of peak torque, and 55% of continuous torque. The servo drive itself, thermal capacity 40%, average current 40%. Everything else is pretty much in line. The gearbox looks pretty good, but once again I wanted to do a 10 to 1 gearbox. So let's see if we can force it into there by hitting the plus sign. Okay, so now we have a 10 to 1 gearbox. You can see that our thermal of our motor went down as well as the thermal of our capacity. This looks like a pretty good match, so let's go ahead and apply. Come back to our components. So we're pretty happy with this solution. So let's start setting the configuration. So as we did before in the last video, we want to go in and set the configuration of the gearbox. Once it comes up, you'll see we have an MP025, SMF1, 10 to 1, and the 0C1 selection. Go ahead and select that. Save it to your axes. Let's now set the motor. As before in the last video, the C is single turn, the 1-2 is no brake, whereas the 1-4 is with a hold and brake. So we know on a vertical load we want to hold and brake, but I also want to use absolute feedback. So let's go ahead to page 3. And here you can see the VPL-B0631 T as in Thomas -PJ14AA. The P is absolute feedback, and the 1-4 will give us the hold and brake we want. So let's go ahead and select that, and we'll save it to our axes. Okay, so next let's set the drive configuration. So once again, as in before in the last video, we had a 2098, we have the -H003-ERS2, which is a SIP safety controller, whereas the 2198-H003-ERS is the standard hardwire safe off. Let's keep everything the same, so we'll go ahead and select that one. Okay, so let's add some cables. So go ahead and select the cable, change your units to meters, because our cables are always in meters. On the last sizing for the belt, we did a 15-meter cable, so we'll use the same. The VPL motor is a single cable for both feedback and power. You can go ahead and select the flying lead. Now in this case, because the vertical is moving on the horizontal, we want to use continuous flex cables. So the very first option we have is a 2090-CSBM1DF-18AF15. This is a 15-meter 18-gauge high flex cable. Let's go ahead and select that. Okay, let's just take a quick review of our performance again. So you can see that our thermal of the motor is in check, the thermal of the drive is in check, the average and peak currents of the drive is okay, compatibility of the motor to the drive is okay, and we're sitting pretty good with the gearbox selection. So now that we're happy with all that, let's continue to the project. Alright, now we want to analyze the power to make sure we have any regen going on. So now we're going to go ahead and click on the share, the axes. We're going to add the axis we just put in there to the first axis. We want to do the DC sharing and shared control power. Hit the save button. Okay, so after it's gone ahead and done its calculations, you can see we still don't have enough regen to worry about adding a shunt resistor to the system. If we scroll down, you can have a better view of the two axes and what they're doing on the DC bus. Now, random is always the worst case. However, if axis 1 was running first and then axis 2 was synced to it, you would simply change the random to manual enter, and then I can sync axis number 2 to axis number 1, and I can put in a time delay. So in this case, I believe we were doing about a 1-second move. So that means that while the belt system is moving, the vertical axis is not. Hit the update button. You can still see that we don't have to worry about any regen. The internal shunt resistors of the units themselves can handle it. From here you want to go to the selected products, and you can see where we've added our second servo, the vertical axis servo, to the belt servo. The show button will show us the cable that we selected, and there's your bill of material to send it into Gerrie Electric to be quoted. Thank you for watching.